All right, let's continue with the story, the history of science. And last time, as you recall, we talked about science in antiquity in the Middle Ages. And remember what the points were? It was that science had a kind of a perils of Pauline existence and had just barely survived a couple of times when science could have been run over by the train and disappeared. And then we also talked about how odd it was that science began in Greece, and instead of going straight to Europe, it went all the way out into Asia with Alexander the Great, came back with the expansion of Islam through Spain, and finally got itself back to where we think of the beginning of modern science being, which is in Europe. And then third of all, we talked about what I was calling categories. And you know, I realized that a better word than categories for what Plato and Aristotle was talking about are universals. If I had that class to do over, I would have changed that to read universals. Maybe that's a more obvious word. So that's where we were. And I did want to stop and thank you all for your talks that you gave, which I just found absolutely fascinating. I learned all sorts of things, right up to the very end when I learned about skinheads, and very fascinating, actually, point of how people aren't necessarily what you think they are or what the media portrays them are. So from the beginning with stinky tofu to the end with skinheads, it was just great. So I think let's all give ourselves an applause. Yeah. And I think that if that is your first or one of your first public talks, hopefully now you've got some confidence that you can do it well in the future. The PowerPoint presentations were great. So was the one chalk presentation. And so
one other besides me.
One other, two. Okay. So chalk still works. But they were great. Thanks so much. So let us go on now and do a second of three discussions of the history of science. So everything we talked about on Tuesday you might call proto-science. It starts in Greece, or maybe even before that in Samaria with some observations of the stars. But really in Greece they first started thinking in a rational way about the world that we live in, and that's what has come down to us through many adventures to be modern science. And so what we're going to talk about today is what happened in Europe in early modern times, which we say 15th, 16th, 17th century, something like that, 18th century. And then on next Tuesday, at the optional lecture on Tuesday, I'm going to talk to you about what happened in the 20th century, which is where the science that I got to be involved in was taking place. So let's see what happened. So people will always talk about what they call the scientific revolution. It was a change. It was a what would you say? It was sort of the wholesale arrival of those early Greek ideas into the modern world. That the way you find out about nature is by asking questions with experiments or observations, and you see what nature tells you, and then you make up a theory to explain it. And then you go out and do some more observations, and maybe that theory is on the right track, or maybe that theory just fails and you have to get rid of it. It's a very odd way of learning about how things are, and very, very unfamiliar, I would say, to most of the people who have ever lived, who did not get their understanding of nature by observing nature, but rather by, somebody in authority telling them the way it was. So let's see how that happened. And what you'll see on the diagram in front of you is the upper half is about what's usually called the scientific revolution, and it is usually taken to be a development in astronomy and physics, not in geology. Although my Portuguese friend Henrique Leitão and I have a paper out now that argues that the scientific revolution was every bit as much about geology as it was about astronomy and physics, and I'll show you why that is in a moment. it shows you there something that says Ptolemy's epicycles. And we had that in the previous mind map. And it shows what you have to do to explain the motion of planets if you have a universe in which the Earth is at the center. Because let me show you what you'd see if you went out in the night sky. How many of you have ever spent any time in a really dark sky, far from any lights? About half. It's different, isn't it? It's completely different. So if you have never been away from city lights at night, you owe it to yourself to go sometime and see what's out there. And here's what you would see. If you looked at the sky, you would see a bunch of stars all over the sky like that. And some of them would be brighter and some of them would be dimmer, and they're what we call the fixed stars. Fixed in the sense that this pattern never changes. I mean, this star is always here relative to these other ones around. They never move. So those are the fixed stars. Of course, the whole thing appears to go across the sky at night and come up the next night because the Earth is rotating. But these are stars that are so far away that even though they are moving, they're moving so slowly that we don't see any difference at this distance. And then you would see other stars in there, and this star would do something funny. This star would start out here, and now we're talking of over a period of months. If you went out and looked at it every night and saw where it was, you would see that it traces out a track that goes across here. So these are not called fixed stars. These are called wandering stars. And the Greek word for wanderer has something to do, it sounds like planetes. So these are what we now call planets. So these are wandering stars. And if you'd see this thing, it would go along like this, and then it would slow down, and then it would make a turn, and then it would get real bright like that, and would go backwards for a while, and then it would turn and slow down, and then it would go off like that again over a period of months. So these things called wandering stars or planets would have these strange loops in them. And so the problem for the early astronomers was, how do you explain that? Okay, so here's the way they did it. They did it with these things called epicycles. They were constrained, they were forced, and I'll tell you in a moment why. They were forced to say that the Earth is at the center of everything. And this wasn't just being foolish. There was a good argument why this was the case. But with the Earth at the center, if you're going to explain this pattern, these retrograde loops, you can do it by using epicycles. So look at this picture for a second. Let me explain it to you. See, there's the Earth at the center, and then there is a dashed circle that goes around the Earth. That's called the deferent. And in the way that Ptolemy explained it, and a lot of the other early astronomers, nothing physical went around the deferent, but the center of another circle called the epicycle went around. So you can see the epicycle is with the short dashes is centered on that dashed deferent. So what they thought was going on was that each planet was on an epicycle, and so it rolled around. At the same time, the center of the epicycle was going around the deferent. So picture, here's the deferent. Here's Earth in the center. Here's the deferent like that. Now you've got an epicycle here, and it rolls around, and the planet is on that. So you see, it comes along. Now picture the center is moving that way. So this thing goes along, and it traces out something like that. Isn't that cool? And what that means is that if you're sitting here at the Earth and you watch one of those wandering stars, it comes along, it goes in this direction for a while, and then it slows down and it comes back, and then it's brighter because it's closer to you, and then it goes backwards for a while, and then it rolls off and goes this way. So this pattern that you see in the sky is beautifully explained by epicycles. And we know now that that's wrong, because the Earth isn't at the center. The Earth is one of the planets. But the cool thing is that when I first found out about this, I thought, well, that's just a silly idea. How could they ever come up with something as ridiculous as that? But what you find is if you make a plot of the solar system the way we know it is, you always draw it with the sun at the center. So now that's epicycles. Here's one with the sun. That's the sun shining right there. And now here's the Earth. And here's, say, Mars going around like that. And what will happen is if you draw this thing and make everything move around and you change the coordinate frame so that your coordinate frame is no longer on the sun, it is on Earth. If this now becomes the center, and then you see how everything else moves, what happens is, sure enough, Mars goes around in a series of epicycles like that. So really, this and this are the same. It's just with a change of the center of your reference frame. So that's how they were doing it, and that was Ptolemy's epicycles. And you're going to need your pencil there to correct something. In fact, I've corrected some things here already, but that says from Greece through, it should say from Greece through Islam. Because remember, that Greek science, which was not welcome in the early Christian world, survived and flourished in the Islamic world until eventually it got back into the Christian world later. That's what we talked about on Tuesday. And you remember there was Aristotle. And Aristotle, remember, he was the one who said that categories or universals are just names. They're not real things, they're just names. I also mentioned that he had the wrong physics. His physics turns out to be wrong. And here was the way Aristotelian physics worked. You see the little sailboat there? And the idea was that if you were to climb up to the top of the mast of a little sailboat and drop something off it, a rock or a weight or something like that, well, the sailboat's moving along, right? So the rock or whatever it is ought to fall diagonally backward because the sailboat's moving forward. See how that picture goes? Is that your experience of how it works? No, it isn't anybody's experience of how it works. So I don't quite understand how Aristotle thought that. Maybe he never went on a sailboat or something like that. But that was because he didn't understand momentum. He didn't understand that the rock is moving forward along with the sailboat, so that as it falls, it doesn't fall backwards. It falls right straight down the mast. So anyway, that was the way things were leading into the beginning of the scientific revolution. The sun was, the Earth was at the center, planets went around epicycles, and we had some really incorrect physics. Okay? All right, we ought to mention Leonardo, just because Leonardo da Vinci was such a transcendent genius. And when you read his notebooks, you just say, oh my God, that guy observed and saw everything. And of course, he drew it beautifully. He understood so much. But he's not part of the history of science. Do you know why? He didn't tell anybody what he found. You know, we scientists are sort of professional blabbermouths. You know, if we find something out, we got to rush and publish it as soon as we're sure it's right. But Leonardo wasn't like that. He didn't want anybody to know what he was finding out, so he developed the ability to do mirror writing. And so people in those days, they didn't figure out how to write it. So all of his notebooks are written in mirror writing so that nobody but him could read it. Nowadays you can read it, and when you see what he was observing, you think, oh my gosh, he saw everything. But he didn't have any influence, or very little influence, down into the subsequent developments, because nobody knew what he was thinking about. After he died, it all died with him, except that now we can read the notebooks. So mention him, but now let us come to the 6 people who are usually the ones most associated with the scientific revolution. It's sort of become traditional to say that at least 5 of these, and maybe the 6th one, Giordano Bruno, they were the people who made the scientific revolution happen. And of course, it's always thought of as a development in astronomy and physics. So let's look at these guys and see what they did. It's interesting. They were from different countries. Copernicus was what nationality? Anybody know? Polish. Tycho Brahe was what? Danish. Giordano Bruno was Italian. Kepler was German. Galileo was Italian and Newton was English. So this was something, this is a beautiful thing about science now. It's very international, and if you become a scientist, you will undoubtedly have friends and colleagues all over the world. It's a really neat sort of fringe benefit of being in this line of work. So let's talk about these people. So here's Copernicus. So Copernicus, you see, goes back 1473. He died in 1543. And in that same year that he died, his great work was published. It was called On the Revolutions, by which he meant the revolutions of the planets around the sun. And he was a Catholic priest in Poland. And maybe he thought it wouldn't be such a good idea to publish this stuff. So he was in no great rush to publish. And the story is that as he was lying on his deathbed, the first printed copy of his great book was shown to him. Well, it didn't upset too many people for a while because nobody could figure out what was in it except a few other mathematicians, because it was extremely dense, technical, mathematical stuff. And you almost had to hunt around for it to find out that the Earth was not at the center. I need to tell you about what Enrique Letao and I are saying in the paper that we've just published. We're pointing out that Copernicus and the Copernican or scientific revolution is always thought of as a revolution in astronomy and physics. We think it's a revolution in geology as well, because there are two ways of stating what Copernicus was telling people. The first one is called the heliocentric universe. Heliocentric, the sun at the center. So it's this picture here. So this is the Copernicus picture with the sun at the center. And that's what everybody always thinks about. And by the way, it's wrong. The sun is not at the center of the universe, is it? The sun is a minor star in the outer fringes of an ordinary galaxy among 10 to the 11th other galaxies. So the heliocentric universe is wrong. If he'd said the heliocentric solar system, that would have been another thing. But people talk about this. That's wrong. But he doesn't talk about it very much. Actually, what he talks about most in his book is the planetary Earth. And did I mention this to you before? If you think about what the word planet means and what the word Earth means, or what they meant to somebody back then, before Copernicus, they had nothing to do with each other, right? What is Earth? It's what you walk around on, and it's what you grow plants in, and what maybe you build your house out of some portions of it. Trees grow in it. It's one of the four elements: earth, air, fire, and water. That's what Earth is, right? What's a planet? Well, a planet is a light in the night sky that goes in this funny pattern. So they've got nothing to do with each other. This is, to my mind, geologically, this is what's so important about the Copernican revolution. Before Copernicus, planet and Earth had nothing whatsoever to do with each other. They had, maybe I told you this, they have about as much to do with each other for somebody before Copernicus as, let's say, Pangea and the key of B flat minor. They got nothing to do with each other, right? So then after Copernicus, people realized, wait a minute, Earth is a planet. And it utterly changed everything. It would be as if we were to discover today that Pangea was written in B flat minor. It is that incomprehensible. So anyhow, that's Copernicus. And he revolutionized astronomy and physics, but also that's what you needed to have geology, because you couldn't possibly have a science of the Earth until you realized Earth was a planet. All right, so now let's go on. So 3 years after Copernicus dies, there's this nobleman in Denmark who's born, whose name is Tycho Brahe. Tycho, they say in Danish. Anyway, we all say Tycho. And he was a fanatic observer. and didn't have telescopes. Remember, Galileo invented the telescope, and Galileo wasn't born yet. So he was making his observations with just his naked eye, and he'd figured out real nice instruments that you could sight along this one, and you could find out exactly what angle that planet was on any given night. And so he made absolutely the best observations of the positions of the planets as they tracked along these funny loops. He was a really fascinating character. He was a nobleman, and he was very much in the favor of the king of Denmark at the time because he cast horoscopes. And he could tell a king what was going to happen in the future and what was a good day. And of course, he needed really accurate measurements to do this well. So the king provided Tycho with an island. It's now in the strait between Denmark and Sweden. And he built this incredible observatory, and it had all these amazing adventures. He had a silver nose. And the reason he had a silver nose was because his own nose had been cut off in a duel. Now you might well think that a young nobleman like that might have lost his nose in a duel over the favors of a young lady, perhaps. Not so. It was a duel over a fine point of mathematics. So this is an interesting guy. And he made these incredible observations, and as he was getting along in years, he made the mistake of not keeping up his good relations with the king. And when the old king died and the new king came along, the new king wasn't interested in Tycho and stopped the subsidy, and the observatory fell into ruin, and Tycho had to leave, and so he went off wandering around Europe. I imagine clutching with him his books in which all of his observations of all of these planets over so many years were kept. And one of the places he went to was Prague, in what is now the Czech Republic. And there, realizing that he didn't have much longer, he met a young German mathematician named Johannes Kepler. And somehow or other, I don't know the details, but somehow or other, Kepler decided to entrust his precious observations to this young mathematician to try to make sense out of them. I'll get this right. Tycho was still thinking in this system. He was still basically a Ptolemaic astronomer. He hadn't accepted this yet. So he gives his stuff to Kepler and then passes on. And Kepler did the most amazing things with it. Kepler analyzed these data, and it was basically Mars. Mars was the most important thing that Tycho had observed. And Tycho had made these incredibly accurate observations, and Kepler had to make sense out of them. And he tried to do it with epicycles. I just couldn't make it work, and he tried all these different adjustments. He tried changing. Well, he said everybody thought that everything was circles in the sky. This went all the way back to antiquity, and the reason was that obviously God had made the universe, and the circle was the perfect figure, right? And clearly God would have made things with a perfect figure, and so everybody had done all the epicycles, the deferents, they were all circles. Although sometimes they would move the center around a little bit, but they were all perfect circles. And Kepler tried to make sense of this, and finally he was able to show that planets don't move on circles, they move on ellipses, as you probably know. And that the sun is at one focus of the ellipse. Remember, an ellipse looks like this. And this is an elongated one. I've exaggerated the lengthening. And the ellipse has two foci, one here and one here. And the sun would be at one, and there's nothing at the other one. And the planet moves around it like that. Okay? So Kepler developed 3 laws, and they were all based on the observations that Tycho had made. And I'm showing you there, real generally, the first one, Roman 1, is that it's not a circle, It's an ellipse. That all the orbits are ellipses. That was the first law. The second one was that if you followed this planet around, and you say, here's the planet, and it goes from here to here in a certain interval of time. I don't know, maybe that's a month or something like that. If you draw lines from the beginning and end to the sun, and you take the area under here, the area swept out in any given interval of time is the same no matter where you are. So you see, then if the planet's over here, it's farther away, so you have to have a narrower triangle in order to have the same area. So what that means is that here the planet is going faster because it goes this distance in the same length of time it takes to go a shorter distance out here. So that was the second thing that Kepler figured out. Nobody would have imagined this. I can't imagine how he figured this out. Incredible. Then the third one has to do, which I've got there as a little formula, it has to do with the difference of if you have two planets at different distances circling the same star, the same sun. So anyhow, Kepler figured all of those things out, and I thought one time, I'm going to go find that in Kepler. So we happened to have a series of books at home that had Kepler's treatise in it. So I went to find it. It took me many, many evenings even to find these things. They were just sort of buried in there. Because when you read Kepler, he tells you all the things that he tried in order to make sense out of these observations. And some of the things he tried are quite remarkable. You say, how could anybody ever imagine such a thing? And yet, somehow, showing that all of these other observations or hypotheses, or all the other hypotheses were wrong, he eventually found the right one, which is those three called Kepler's three laws. And the only reason he could do it was because Tycho's observations were so amazingly accurate. Okay, up at the top there, I've got the sixth guy, Giordano Bruno, who is sometimes included in this pantheon and sometimes not. And he was an Italian. He was a churchman, but one with a very independent mind. And he was not constrained by religious dogma the way almost everybody else was. And he came up with an idea which Carl Sagan later said, this is the most important thing that's ever been found in science. And Carl Sagan said one time, if you knew there was going to be 1,000-year dark age, and all learning was going to be lost, and you could somehow pass on to the people 1,000 years into the future one piece of knowledge. Who was it last night talked about atoms? Was it, yeah, okay, you said that, that the most important thing would be to say that everything was made of atoms. Who was it who said that? Richard Feynman. Okay, so that's Feynman's pick. And Carl Sagan's pick is he would have said, tell the people in the future that every star in the sky is a sun very far away. And so one time I thought, well, that's interesting. Carl never said who came up with that, so I thought I'd try and find it out. I had tracing it back through the literature, trying to find who first said it. And it turned out it was Giordano Bruno who first said it, right in the middle of the scientific revolution. Well, he said a lot of other things that got him in bad trouble, and he ended up burned at the stake in Rome. And so many of us scientists think of Giordano Bruno as a martyr for science, but it is worth noticing that he wasn't burned for that. He was burned for various other things that the church considered to be heresies, but not for that in particular. So anyhow, Giordano Bruno was not, I don't think you could call him a scientist, you would call him a visionary. He had a real good intuition about what was coming. I mean, the idea that every star is like the sun, only far away, is an incredible thing to think of. Okay, so now we've got Kepler has made sense out of Tycho's observations, and now we come to Galileo. So here's our Italian guy, and he made all sorts of contributions. And one of them was to invent the telescope. In a sense, he reinvented it, because the story I've heard is that the telescope was first invented in Holland, but people in Holland used it for looking at ships in the distance. They didn't turn it on the sky, and somehow word of this invention got to Galileo. Somehow he said, they discovered in Holland that if you put two lenses together, you can see things bigger. And so he immediately reinvented it based on that and turned it to the sky and started seeing these amazing things. So here, let me draw a little bit bigger the one that I've sketched in there in a schematic way. So Galileo turns his telescope on the planet of Jupiter, which is bright in the night sky. So here he sees Jupiter like that. Imagine that's a bright spot in the night sky seen through the telescope. And then he sees 4 more little things that nobody had ever seen before, because the naked eye won't do this. You can only see it with a telescope. And they look like this. What on earth could those be? Moons, right. And here's how he figured out that they were moons. If he saw it one night there, I'll just draw the next night here, he'll see they're all in slightly different places like that. And the next night, there's something like that. And now there's 3 over there. So he watched it night after night, and he kept track of this pattern. And then what he did was to plot them here. He plotted them, roll and take note, he plotted them on chronozoom, with Young getting that way. And let's say this is up, we'll call that plus y, and this is minus y. So plus y and minus y. And this is where Jupiter is. And basically what you would find is if you could watch one of these things, and over the nights it would go like this. And so you could draw a line through there, and that's what happens, of course, if you see a circle. If you're looking end on a circle, and then you kind of trace it out that way, it will look like a sine wave. So that was one of them, and here and then there was one that was further out that went like this, and then there was one in close that went like this, and so forth like that. And each one you could plot those curves, and they would be based on where each of those little moons were. So what did that tell you? That told you that those moons were going around Jupiter, right? They were circling around Jupiter. Does that bother you? Doesn't bother you. Imagine that you were somebody else and Galileo told you about this. Why would it bother you? I have a drink of water while you figure out why it would bother you. Michelle? Jupiter was a planet, right. And what do planets do? They revolve around what?
I don't know.
In those?
Planets were just, they wander around.
Well, they wander through the sky, but why is it that they wander through the sky, Paul?
They wander around the Earth.
That's right. So for everybody at that time, all planets go in a circle around the Earth. And not only that, the moon goes in a circle around the Earth. Not only that, the sun goes in a circle around the Earth. Everything goes in a circle around the Earth because the Earth is at the center. And it is the nature of everything else to rotate around the Earth, to revolve around the Earth. That was the view. That's this view here. All of a sudden, Galileo is saying, wait a minute. There's some things that revolve around Jupiter. See how that, if you thought that the Earth was something enormously special, it was the center of the universe and everything revolves around it. You might know some people who think everything revolves around them, but in those days, it was the Earth and everything was supposed to go around it. Here were some objects that were revolving around Jupiter. Think what a shock that is. I mean, that's a terrible thing to find out. And so there's a story that may or may not be true about a cardinal who refused to look through Galileo's telescope because he didn't want to see any nature doing something that was as impossible and horrible as that. So it forced people to think in a new way about things. So that's Jupiter's moon. And the other thing is Galileo fixed a lot of the things that were wrong about Aristotle's physics. So he understood the reason that if you drop a stone from the top of a mast on a moving ship, it falls straight down the mast, is because both of them are going this way together when you start, right? So he got much of that right, and then he was a great propagandist for this. He had, one of his books is called A Dialogue Concerning the Two World Systems. And the two world systems are the old system of Ptolemy and then the new one of Copernicus. And what Enrique and I found when we were working on our little paper about the scientific revolution being geological as well as astronomical is there's a great quote from Copernicus that I would have brought in if I'd thought to do so, but it's something about how we have taken the Earth from just being at the bottom where all the bad stuff falls to, and we've made it be a planet in the sky. We've sort of made the Earth be important, and so it was a whole big change, and then finally it all gets wrapped up with the Englishman Isaac Newton, and Newton made sense at last out of Kepler's laws and Galileo's observation and Copernicus' model of things, and figured out the physics. So there are a couple of the great laws of Newton. And his physics was so good that at last you could predict eclipses exactly right. So the reason now that you can be told that there's going to be a solar eclipse on such and such a date in such and such a place, and you go there and it happens exactly in the place the astronomers say and exactly at the time, is because Newton's laws are right. Turns out they're incomplete because Einstein showed that if you're moving fast enough, things change. But at the velocities that we deal with or in the solar system, Newton's got it right. Okay, so this was an enormously prestigious thing. Newton's prestige was gigantic. He was the first great international scientific hero. And I love this this quote down there from Alexander Pope. This was a eulogy or an epitaph for Newton when Newton had passed away. I think he's buried in the Westminster Abbey. Isn't that where they're having the big wedding tonight? Anyway, isn't that right, Millie? Westminster Abbey. The Prince who is getting married? William? That's right, that guy. At any rate, the important thing in Westminster Abbey is that Newton is buried there. And here was Pope's epitaph, and listen to this because this got a wonderful double meaning in it. He says, "Nature and nature's laws lay hid in night. God said, 'Let Newton be,' and all was light." Boy, now there's a glorious epitaph. Okay, we're going to move on, but first of all, how about take a moment just to refocus. Excuse me? I'm just not hearing you.
I'm sorry, Galileo's imprisonment, just sort of how he was received at the time.
Yeah, I don't want to talk about it. Yeah. Got him? Thanks so much. Why don't you give those to Roland? He's going to take them up to the thing. Thanks. Okay, are you ready? Well, part of my theme for today is up at the top of the mind map. It says a puzzle for the next 2 lectures. Earth's health is at dire risk. So geology may be the most vital science for the 21st century. So why is geology a low prestige science? What history lies behind the status of the different sciences? If people talk about sciences, they talk about the sciences. You know, what does it start with? Physics, maybe mathematics, then physics, chemistry, biology, astronomy, right? Oh yeah, and then there are those guys that go out with rock hammers, and I think they dig up old cities or something like that. What are they called? Geologists, something like that. Maybe they're geographers. I don't know. They don't. So geology just doesn't have high status, and that bugs me. And I've tried to understand why that is, and I think it's not just my personal feelings being hurt, even though that matters obviously, but what is really too bad is that if we screw up this planet and make it so that it's not fit for human life, well, we're in really bad trouble. And who knows about that? Well, partly it's ecologists like Ryan, but also it's geologists like me. I mean, we're interested in the Earth. And so you would think that our science ought to be right at the top in terms of prestige, in terms of funding, in terms of public concern, in terms of what we're able to contribute. And yet somehow geology is this afterthought when you come to science. I hope my colleagues don't hear me confessing this, but at any rate, I think maybe we can understand a little bit about why that was if we now get away from the scientific revolution and start thinking about the emergence of geology. Okay? So let's do that for the rest of the time. So on the left, I've got down there is a reminder to you, something that we talked about earlier in the semester, and that was that the Portuguese and Spanish voyages of discovery really changed the way people thought and investigated in the late Middle Ages. And in fact, our understanding of the Earth was utterly different after 100 or 150 years of Portuguese and Spanish voyages. We've already talked about that, but I do want to show with a gray line that comes out from the front of that little ship, that little caravel, and goes over there to the center, to meta-scientific discoveries. And remember, I talked about these. Meta in this sense means beyond. These are the discoveries that make it possible to do science. These are the discoveries that are greater than any particular theory, even the really wonderful ones like evolution or quantum mechanics or relativity or Newton's laws or plate tectonics or any of those. These are the discoveries that are even more fundamental to science than any of those. And for me, I've talked to you about this before, first of all, nature is orderly, it's not capricious. Remember, those Portuguese sailors would sail out into the middle of the Atlantic Ocean to take advantage of winds, convinced that the winds were going to do what the winds do, and they weren't going to suddenly blow straight down and sink the ship, right? The second one is that you can have a conversation with nature through experiment or observation. You ask a question, you say, what's going to happen, nature, if I drop this pencil? And you drop it and you see what happens, right? And of course, many experiments now are extremely complicated and sophisticated and subtle, but basically what they're trying to do is to find out what nature does, what are nature's laws. And then the third one is that nature's language is mathematics. And nobody knows why that is, why it should be that you can understand how the universe works in terms of complex, sophisticated mathematical equations. And that's the way it is. Nobody understands why that is. So that's the third great meta-scientific discovery. And then the fourth one was that observation wins over authority. And if you remember back to the Portuguese voyages, Aristotle was authority, and he said there were 5 climate zones on the Earth, and when the Portuguese went and looked, they discovered there were 7, and so you had to change things. Anyway, I just want to bring that in and remind you of what we spoke about there before. But let's come back now to what everybody recognizes as geology. Enrique and I recognize the Portuguese voyages as geology, but most other people don't yet. Anyhow, let's look at the people that would turn up in a book about the history of geology. So we'll start with this guy, Nicholas Steno, and I think you read about him in the Mountains of St. Francis. He was the Danish anatomist who ended up in Florence and in the mountains of Tuscany, or the hills of Tuscany, figured out the principles of stratigraphy. What seems pretty simple-minded now, that if it's on top, it's younger, but that wasn't obvious in the 17th century. And basically, Steno was the guy who first figured out how to read history written in rocks. And of course, he was highly influenced by religion, and ended up as a cardinal, no, not a cardinal, as a bishop, and ended up as a missionary to these Protestants who had revolted. I need to pause for just a second here and say something that I'd forgotten to mention. You see that heavy dashed dot line that runs down through there? It's on 1600. I found that for my own personal understanding of the history of science quite a number of years ago, I realized that I could take 1600 as my personal date for the scientific revolution. And it happened to be the date of the burning at the stake of Giordano Bruno. It was also the date on which Tycho handed his observations to young Johannes Kepler in Prague. And it seems like a good boundary date, and you might want to use it as your personal date. Anyhow, I've built this thing around it. Ryan, you were going to say?
Yes. Thinking about observation winning over authority, I mean, I know that a lot of these people are fairly well off, and could afford to, not be working in the fields or whatever, and instead inventing telescopes and whatnot. So my perception of science, as it gets practiced through the 19th century, is that it's only fairly wealthy individuals who are doing it. So it's still a small group, but I wonder if it's true that with observation winning over authority, you get some degree of democratization of knowledge, that anybody can go out and do an experiment. And I wonder if the participation in science rises a lot over time. Have you thought about that at all?
Not in exactly those terms, but I think your point's well taken. I mean, if you look around right now, there are surely more scientists on the Berkeley campus today than there were in the whole world when these guys were working, right? And so I think it has been democratized a lot. And I suppose another thing that's changed is what you say is right. In the 17th, 18th, 19th century, science was primarily practiced by those who could afford it, who were independently wealthy. Now it doesn't take independent wealth; it just takes intelligence and a good education. What were you say, John?
Well, we
Yeah.
outsource. I mean, we give government sponsorship for these things.
Mm-hmm.
Without government grants, it would go right back to that.
Yeah, and we'll talk about that on Tuesday, because in fact that didn't even happen until 1945. Yeah, right after the Second World War. Katie?
I was going to say, before it was a church grant instead of a government grant that would allow these people to work, and so a priest or a church official would do it because they had the access to the wealth at the time.
Mm-hmm. And maybe some leisure too. So my friend in Piobico, Father Domenico, who collects ammonites, that's his hobby, and he gets paid for being a priest, but that's what he does when it's not Sunday, right? Yeah. Uh-huh. Interesting points, yeah. Okay, so anyhow, let me tell you where this is going as an explanation of why geology does not have this great prestige that, say, astronomy and physics clearly do. I'm going to make the point that geology is, I'm not going to say harder, I'm going to say it's more complicated than either physics or astronomy. What people do in physics is they design their experiments so that they focus on one effect. If they're dealing with something complicated, they will figure out how to get one effect so that it doesn't influence their experiment. There'll be some other physical law, and get rid of it. We'll focus on one thing. And you're able to do that in physics because you can isolate these things. You're dealing with something right now. For example, in physics, if you have an electron that's moving through your apparatus, it doesn't make any difference at all what that electron was doing yesterday or a million years ago. An electron's an electron, and its history doesn't influence. It just is, and it does what electrons do, and all electrons do the same thing, right? In geology, with this huge historical background, here comes big history, with the historical background of everything in geology, everything you see is influenced not just by the laws of nature, but by the particular history that it's gone through. So if you go into the Apennine Mountains and you see these mountains, they look the way they do not because of the laws of physics, that influences, but also because of 100 million years worth of history that all of those rocks have gone through. And so where we're going with this is to make the point that it was just harder for geologists to figure out their subject because they had all of these complications, from all of these historical complications. Okay? So, a few of these other people. So here is James Hutton, who is was a Scotsman, and he's usually credited with being the person who figured out deep time, that there had been incredible amounts of time. And that was influenced partly by religion, but it was also influenced, and you see there's a long gray line coming over from Isaac Newton that says infinite time. For Newton, the cycles just went on and on and on and on and on as the planets kept going around the sun in ellipses, right? And there was no reason to say that that had ever started. Nowadays, we know when it started. It started, remember the number, 4.567 billion years ago? We know when it started. But Newton couldn't tell that. Newton didn't have the information to figure that out. And so Hutton was, in his invention of deep time, was influenced also by Newton saying that these things just go around and around and around, and there's no stopping them. There's no obvious time for us to start. So, to my mind, it's interesting to see what these early geologists were doing and what the influences were on their thinking. And so Newton was definitely, and Newton had that prestige, you know, God said, let Newton be, and all was light. So the guys who are inventing geology now have got to be influenced by the prestige of Newton. Okay, so there's another guy there whose name is a wonderful, full name is Abraham Gottlob Werner, and he was a German mining engineer, I guess you'd say, and he looked at rocks much more closely than almost anybody else did, certainly much more closely than Hutton. And the history of geology, early history of geology, is commonly presented as a conflict between James Hutton and Werner, Abraham Werner. And the reason that they're usually put on opposite sides is that Hutton correctly figured out that basalt had once been molten and had cooled. And Werner thought that basalt had been deposited as a precipitate out of seawater. So Werner got that part wrong, but he got some other parts right. But I think it's amusing to me that most young geologists, at least in the English-speaking world, are taught that Hutton was a hero and Werner was a sort of, he got it all wrong, you know. And I suspect that may have to do with the fact that histories of geology written in the English language were primarily written by Englishmen. And Hutton, well, he wasn't quite an Englishman, he was a Scotsman, but that's close enough. That's better than a German, for heaven's sakes. And so those books are usually written with Hutton as the hero and Werner as the villain, which I think is a terrible shame, because Werner's work, it's now been shown by a historian of science that Werner then went, his ideas led directly into the evolution of mineralogy, which is an extremely important part not only of geology but of solid state physics. So we should honor both of them. Okay, then we come to an interesting guy who sort of contradicts what Ryan and John were saying back there, and that's William Smith, sometimes known as William Strata Smith. And he was a guy who was born in England in impoverished circumstances, never had enough money, but he was smart and somehow got an education as a surveyor, and got hired to survey mines, because now you look at this, we're sort of 1800. He was active around 1800. This is the beginning of the Industrial Revolution. So in England they're using lots and lots of coal to power steam engines to do the things that they did in the early Industrial Revolution. So William Smith was hired to survey coal mines. So he spent a lot of time underground looking at rocks. And he was also hired to survey canals, because in the early Industrial Revolution, the way you got your coal from the mine to wherever it was going to be burned in the factory or something was on canal barges. The roads were terrible in those times. There weren't any railroads yet. But if you got people out there and you dug a canal and you kept it right along the contours of the hillside, then the water would stay in there, and you could then have a boat, and usually there would be a tow path along the side, and you'd have horses or mules or something that would tow the boat along. And so most of the transport in those days was done by canal barge. So you needed guys who really understood surveying to lay out the canal, because it has to be exactly on the same horizontal contour all the way, or else the water will run down one end of the canal to the other, which isn't good, right? And so William Smith spent time underground in mines, and he spent time in these canal cuts. You know, they'd have to make cuts through the hill. These were maybe the first big artificial exposures where you can go and look at rocks. And to this day, if I see a road cut, I'm ready to go look at it. In fact, Millie and I have an amusing thing that we've observed, and that is that when we're driving along, she sees all the plants and all the flowers and things like that. If we go through a road cut and it's covered by vegetation, and there's one little spot of bedrock like that, I see it. I just filter out all of the plants that she sees, and I'm paying attention to them. They just cover up the rock. So he was one of the first guys to get to do this. And he realized that you could make a geological map, and he made this incredible, wonderful geologic map of most of England. There's a book by Simon Winchester that's called The Map That Changed the World, and if you're at all interested in this, that'd be a good read. So he also realized, he was the first person to realize that you could use fossils to say that this sandstone in this canal cut is the same age as that one over 3 counties away, because they have the same fossils in them. And he didn't understand evolution. All he knew was that rocks of particular ages have particular fossils in them that look, that look as they do, that look different from the fossils that are older and the fossils that are younger. And so that was the beginning of biostratigraphy, or mapping and correlation. And then he says, you see, he operated around 1800, more or less. And his techniques, William Smith's techniques, were so useful that from 1800 to 1850, more or less, a whole group of people, and this was partly in England, partly in France, a little bit in Italy, toward the end, part of it in this country as well, in the Appalachians. These were guys who went out, and they were field stratigraphers. In other words, they went out into the field and they looked at outcrops, either natural ones or canal cuts or something like that, mines, and they started putting together how what were the ages of rocks in different parts of the world. So here, let me come back to my theme for a second. If you are Katie or Paul, you're an astronomer, you've got it easy. You know, you can You probably have to look into a telescope, but if you were an early person interested in the stars, or if you're just you and you're just interested in the stars, what you can do is go out on a warm summer evening and you can lie on your back in the grass, and maybe you take a beer with you, or I don't know, but you watch and the stars go by overhead. And the whole thing goes by. In the course of a year, you can see all the stars, at least in the northern hemisphere. You might have to go to the southern hemisphere to see the southern stars. But they're all just there. And what you're seeing, you can't tell anything about history. Nowadays you can, but early on there were just lights in the sky, and you could see them. If you're a geologist and you want to find out what rocks are somewhere else, you got to go there. They don't parade by you like the stars do. In fact, if you want to know what is 100 kilometers away, you got to go there because you can't see it around the curve of the Earth. And if you want to know what rocks are in Patagonia, you've got to go to Patagonia, right? And so in that sense, it was harder to do geology. First of all, because you had to go to all of these places. Many of them were hard to get to, especially in the 19th century. And they might be full of wild animals and people who didn't like visitors and things like that. And what's more, what you were looking at was just loaded with history. The rocks that you were seeing were there because they'd been deposited at a certain time. They had fossils in them because, well, by this time they're figuring out that the fossils had evolved. And what's more, they're now tilted up on end like that because they were deposited horizontal. Now they've been tilted up. The upper parts have been eroded. More fossils and rocks have been deposited. Very, very complicated because it's all historical. And that's what geologists were trying to deal with throughout the 19th century and on into the 20th century. So my excuse, if you will, for geology is that it just took longer to get the observations and figure out what was going on than it took physicists who could make careful experiments or astronomers who could just look at the sky. Okay, so let's look at this last part in the right-hand corner. The great payoff, I would say, of this phase of geology, up until about 1900, the great payoff is the ruling theory, not of geology, but of biology. Because it was geology that led to the theory of evolution. Charles Darwin was a geologist. He was also a biologist, but he was thinking as a geologist. Remember, if you want to see what's in Patagonia, you got to go to Patagonia, and that's what Darwin did as a young man on the British research ship, the Beagle. They sailed all around the world. It was 3 or 4 years, something like that, and he made all of these observations. But he went to places that were far away and saw what was there. So let's just think a little bit about how you get from geology to biology. So down there I've got Carl Linnaeus, who was, what was he, Swedish? Yeah, Swedish. And Linnaeus was the guy who invented the classification of organisms. So if you're a biologist, you're looking around at you, and there's just an almost infinite variety of plants and animals, just vast numbers of them. And what you see is that some of them kind of look similar to each other. You know, rats and mice kind of look closer to each other than either of them does to elephants, right? And rats, mice, and elephants look more like each other than either one of them looks like a palm tree, right? And so people were realizing that there was this hierarchical ordering of all of the plants and animals. And so it was Linnaeus who invented this system of describing things in a hierarchical manner with species, many species, and then you put some of them together, you lump them into genera, and then those are lumped into families and orders and classes and so on like that. So Linnaeus figured out this hierarchical way of ordering all of the plants and animals, but didn't know why they were like that, because evolution came later. And so then, I think of it, I'm sure this is highly oversimplified, but from my standpoint it works, to say that the time scale which is there, that's PZ, MZ, CZ, that's Paleozoic, Mesozoic, and Cenozoic. That was the time scale that those field stratigraphers worked out. And so they knew what the fossils were in each of those times, and they could see that the shapes of plants and animals had been changing through time. So that was part of the input into Darwinian evolution. The other thing, of course, was Linnaeus had shown that they were hierarchical. How do you get something hierarchical? So it was the genius of Darwin to say that these were evolutionary changes, that there were ancestral forms which had then been modified in various different ways, and that the reason for this was natural selection. That those individuals who have a genetic makeup that allows them to flourish a little better than their neighbor do, they're the ones that survive, and they're the ones that have more offspring. And so we now know, he didn't know about genes, but we now know that those genes get passed on. And so all of this goes together into biology. And I've also put in here Alfred Russel Wallace. You should know him. He was the other guy besides Darwin who figured out evolution at the same time. Gets less credit for it, but ought to get more. Meanwhile, what happens to geologists? Okay, so what we realized, I wasn't here, what they realized was that if you were going to understand the Earth and how it worked, you had to know how it had worked. And it was different in all different parts of the world. Basically, you had to go to all of these places all over the world. You had to map those rocks in the way that William Smith had figured out. You had to find out what the fossils were, what the ages of all the rocks were. You had to see when they'd been tilted. You had to see when lava had poured out. It was a colossal job to do. And so as of about 1850 or something like that, it was the job of the geologists to go out and do that. And it took a long time. It took maybe 150 years to map the world well enough that you'd end up with a map like that one on the wall, including the ocean basins. And that from that map, you could figure out how the Earth had evolved. You could understand that plate tectonics was the guiding theory behind it. So during that 150 years, when geologists were simply going out and finding out what was there, physicists were doing things like, Einsteinian relativity, quantum mechanics. As people have what Einstein said is, I am interested in the thoughts of God. The geologist was interested in what kind of rocks were on the other side of the next mountain, right? And so my feeling is that is why geology got left out of the prestige sweepstakes when the sort of hierarchy and ranking of sciences was set up, which kind of got firmed up around 1900. So what I'm going to do next Tuesday, I hope you'll come, is I'm going to show you what geology has done with this understanding in the 20th and the beginning of the 21st century.